Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is Optimization Part 2. In this video, we are going to discuss the methods. Method 1. This is the first method. We will be using the method used in finding absolute extrema. This is the method we used in the first example also. You can also refer our first video on this topic, optimization. Recall that in order to use this method, the interval of possible values of the independent variable in the function we are optimizing. Let's call it as I. This I must have finite endpoints. Also, the function we are optimizing, once it's down to a single variable, must be continuous on I, including the endpoints. If these conditions are met, then we know that the optimal value, either the maximum or minimum, depending on the problem, will occur at either the endpoint of the range or at a critical point, that is inside the range of possible solutions. Actually, there are two main issues that will often prevent this method from being used. However, first, not every problem will actually have a range of possible solutions that have finite endpoints at both ends. We will see at least one example of this as we work through the remaining examples. Also, many of the functions we will be optimizing will not be continuous once we reduce them into a single variable. And this will prevent us from using this method. Okay, now let's see the method 2. Here is the method 2. In this method, we are going to use a variant of the first derivative test. In this method, we also will need an interval of possible values of the independent variable in the function that we are optimizing I. However, in this case, unlike the previous method, the endpoints do not need to be finite. But in this case, the endpoints need to be finite, right? Also, we will need to require that the function be continuous on the interior of the interval I. And we will only need the function to be continuous at the endpoints if the endpoints is finite and the function actually exists at the endpoints. We will see several problems where the function we are optimizing does not actually exist at one of the endpoints. This will not prevent this method from being used. Let's suppose that x is equal to c is the critical point of the function we are trying to optimize, f of x. We already know from the first derivative test that if f dash of x is greater than 0, immediately to the left of x is equal to c, that is nothing but the function is increasing immediately to the left. And if f dash of x is less than 0, what does that mean? Immediately to the right of x is equal to 0. It means the function is decreasing immediately to the right. Then x is equal to c will be a relative maximum of f of x. Now, this does not mean that the absolute maximum of f of x will occur at this point x is equal to c. However, suppose that we knew a little bit more information. Suppose, in fact, we know that f dash of x is greater than 0 for all x in this interval I, such that x is less than c. Likewise, suppose that we knew that f dash of x is less than 0 for all x in I such that x is greater than c. In this case, we know that to the left of x is equal to c, provided we stay in the interval I, of course. The function is always increasing and to the right of x is equal to c, again staying in the interval I. We are always decreasing. In the case, we can say that the absolute maximum of the function f of x in I will occur at x is equal to c. Similarly, if we know that to the left of x is equal to c, the function is always decreasing and to the right of this, the function is always increasing, then the absolute minimum of f of x in I will occur that point. If I show you a graph, you can understand that. Before we give a summary of this method, method 2, let's discuss the continuity requirement a little. Nowhere in this discussion we did the continuity requirement apparently. We require that the function we are optimizing to be continuous in the interval I to prevent the following situation, this graph. In this case, a relative maximum of the function clearly occurs at the point x is equal to c. Am I right? Also, the function is always decreasing to the right and is always increasing to the left. However, because of this discontinuity at the point d, x is equal to d, we can clearly see that f of d is greater than f of c. And so, the absolute maximum of the function does not occur at x is equal to c. It had a discontinuity at x is equal to d. Not being there is, this would not have happened and the absolute maximum would have occurred at x is equal to c. So let me give you the summary of the second method. First derivative test for absolute extrema. Here is the summary. Let I be the interval of all possible values of x in the function f of x. The function we want to optimize, and for this suppose that f of x is continuous on I except possibly at the endpoints. Finally, suppose that x is equal to c is a critical point of f of x and that c is in the interval I. If we restrict the x to the values from I mean we only consider the possible optimal values of the function, then these are the two conditions that will occur. If f dash of x greater than 0 for all x is less than c, and if f dash of x is less than 0 for all x is greater than c, then f of c will be the absolute maximum value of the function f of x on the interval I. Does this make sense to you? Same way, if f dash of x is less than 0 for all x is less than c, and if f dash of x is greater than 0 for all x greater than c, then f of c will be the absolute minimum value. Do you understand the difference between these two? Then f of c will be the absolute minimum value of the function f of x on the same interval I. So this is all about the second method using the first derivative test for absolute extrema. Hope you are clear with method 2? Okay, now let us look at the method 3. In method 3 we will be using second derivative. Method 3 use the second derivative. There are actually two ways to use the second derivatives to help us identify the optimal value of the function, and both use the second derivative test to one extent or the other. The first way to use the second derivative does not actually help us to identify the optimal value. What it does do is allow us to potentially exclude values, and knowing this can simplify our work somewhat and is not a bad thing to do. Suppose that we are looking for the absolute maximum of a function, and after finding the critical points we find that we have multiple critical points. Let's also suppose that we run all of them through the second derivative test and determine that some of them are in fact relative minimums of the function. Since we are after the absolute maximum, we know that a maximum, it may be of any kind, can't occur at relative minimums, and so we immediately know that we can exclude these points from further consideration. We could do a similar check if we were looking for the absolute minimum. Doing this may not seem like all that great of a thing to do, but it can, on occasion, lead to a nice reduction in the amount of work that we need to do in the later steps. So this is all about the first way using the second derivative. Now second way. The second way of using the second derivative is to identify the optimal value of the function. Is in fact very similar to the second method that we discussed here. The second method. In fact, we will have the same requirements for this method as we did in the method 2. We need an interval of possible values of the independent variable in a function we are optimizing. Call it I as before. We generally call the interval I here. And the endpoints may or may not be finite. It doesn't matter here. We also need to require that the function f of x to be continuous everywhere in I except possibly at the endpoints. Now suppose that x is equal to c is a critical point and that f double dash of c is greater than 0. I mean the second derivative after plugging in this point is greater than 0, a positive one. The derivative test tells us that x is equal to c must be a relative minimum of the function. Suppose, however, that we also knew that f double dash of x is greater than 0 for all x in the interval I. In this case, we would know that the function was concave up in all of the interval I, and that would in turn mean that the absolute minimum of the function f of x in this particular I would in fact have to be at the point x is equal to c. Likewise, if x is equal to c is a critical point and f double dash of x is less than 0 for all x in the interval I, then we would know that the function was concave down in I and the absolute maximum of f of x in I would have to be at the same point x is equal to c. Hope you are clear with all the three methods. These are the information you should know about all the three methods. In our next video, we can see suitable examples for each of the method. Hope you are clear with this introduction part. In case if you get any query, you can let me know. See you in the next video. Have a great time.